Hey y'all, it's your math teacher Mr. Boyden here. Today we're back at it again. We're starting a brand new unit today. We're in calculus and we're moving to our third unit, which is going to be all about integrals. So in the very first week of class, and probably the second video, I talked about how calculus is only two things. It's slopes and areas. Derivatives are the slopes, and we're going to start working on the areas. Now there's a little bit more to it than that. I mean, it's not just areas. There's lots of cool applications and lots of cool consequences from integrals. But today we're going to focus on just areas. We're going to be finding areas. You're probably going to find that it's easier to follow along with this if you have a calculator with you, or if you want to take my word for it, you can. You're going to see me punching in this as I go along today. So with that, let's get started. Okay? Integrals are basically two things. Number one, yep, they're a way of finding areas. But the second thing is they're a way of accumulating y values. They call it an accumulation function. We're going to get into the applications of that a little bit later. We're so focused on number one right now. In today's the specific topic, we're going to be finding what's called a Riemann sum or a Riemann integral. Up here, this is just the notation for it. Okay, and so we're going to get to that a little bit more, a little bit later, and we're going to dive in deeper into the next video. I'll explain a little bit of that at the end of this one. So don't worry about that too much yet. We're going to get there. Okay. So we already know how to find areas of shapes like this. And from geometry class, we know all about trapezoids and rectangles and parallelograms and circles and things like that. We can decompose shapes down into those, but we haven't done a lot of work where we found areas with things that are curved, with the exception of a circle. We know how to do that, but this isn't a circle. And this curve right here doesn't have anything to do with a circle. It looks almost like maybe it's some sort of cubic or something. And so the one thing I want you to notice, we have a function f of x right here. In this one, it's a velocity function. What we're trying to find are these areas underneath the curve that goes down to the axis. So notice, they're both bound. The regions are bound by the x-axis. They go from some number a to some number b, some number a to some number b, and we're not shading above them, it's just below. So that's going to be how we're going to define integrals for right now, is we're going to be finding areas underneath the curves. Okay, and so let's get into our Riemann approximations. The function that's defining this one, this is the natural log of x plus 1. So you may wish to know that as we go through this. Okay, and we're going to use what's called a left-hand approximation. Now, if you're an IB tester, it would be exceedingly rare that you'd be asked specifically for a left hand. You may be asked to make a Riemann approximation, and it's important that you understand the concept, because if you don't, the next videos aren't going to make any sense, and the purpose of integrals aren't going to make any sense. Now, if you're an AP tester, you will specifically be asked for left and right hand approximations. They'll say, do a midpoint rule, do a trapezoid rule. So I've named the four now: left, right, midpoint, and trapezoid. We're going to run through all of those today and see their similarities, differences, costs, and benefits. Okay, so just so you understand what your expectations will be. Okay, so on this one, we're going to have our curve. It's bounded by x equals 0 and x equals 3. Let me put x equals 3 on there. And so those are those values, a and b, those x values from before. Okay, we have that on our picture as well. Okay, so that matches up nicely. And so what we're going to do is we're going to start breaking this up into rectangles. It's an approximation. It's not going to be perfect. And the left hand means when I break this up, I'm going to use the left side of the interval to pick my y value. So what I'm going to do is I'm going to chop this up every 1 unit. And so I'm actually going to start from the right because it's easier to see. So I've got this interval right here from 2 to 3, 2, 3, 1, 0. And so I'm going to use the left side of that interval. Okay, so 2 and 3, the left side is this one. I'm going to use that y value from 2 to make a rectangle. I'm going to go to this next interval, the one in the middle, from 1 to 2. I'm going to use the left side of it to make a rectangle. The left side, y value, make a rectangle. Same with this down here. I'm going to use the left side of the interval, 0, to make a rectangle. Well, it's 0, so it's a rectangle of no height. That's not very interesting. Now remember, what we're trying to do is find areas. And so I'm going to go now and find the areas of these rectangles. And in order to do that, all I need is base times height. And so the base of this one is 1. And what's the height? Well, that would be the natural log of 2 plus 1. That's why I have my calculator here today. So I'm going to type that in, natural log of 3. And I get 1.10 when I round that. Okay, great. Let's go to this one. The width is 1. The height is right there. So my x value is 1, so that's natural log of 1 plus 1, or natural log of 2. And that is 1.69. What about this rectangle down here? Well, it's not really much of a rectangle at all. It's just a line segment, okay? So it has no height on this one. One thing I want you to think about, based on what you see here, if I shade these in, have I over-approximated or under-approximated my area? Okay, and what I'd like you to notice is I'm missing this area, and I'm missing this area, and I'm missing that area. Is there anything I've overshaded? No, I haven't shaded above the line at all. And so this is an under-approximation. Now it turns out that a left-hand approximation will always be an under-approximation for an increasing function, one that's going up, and this one is, okay, so no coincidence. If we want our total area, all we have to do now is add up our rectangles. So I'm going to get 0.69 plus 1.10, and my approximation for that then is 1.79 square units. Okay, so that's my total. I'm just adding up those two rectangles. Pretty simple. Okay, so normally mathematicians want a general way to do this, and so we come up with a general form. It is a sum, so that's what the sigma is about. And then take a look at the notation here. All it's saying, f of whatever, that means it's a y value. So the height, based on the left side of the interval, so this is height, delta x, that's how much did x change, that was the width of the rectangles. Width times height, that's the area. We add up all the areas of all of the rectangles, from 1 up to n, however many rectangles they are, and that gives us our area, okay? And I've got some stuff written down here. If you want to pause the video and read it, it explains the same stuff that I just said, okay? So let's go down and do a right-hand approximation. A right-hand approximation is very similar. We still have the same function, natural log of x plus 1. And so now let's try a right-hand approximation. I'm going to put in these same intervals from at 1, 2, and 3, and we want to find that total area. It's very similar this time. The only difference is now we go from the right side of each interval. Now the only reason I started on the far right last time is because I didn't want to start with a rectangle that had no height. That might be confusing as a first example. Just for consistency, I'm going to start from the right, but aside from a teaching move, there's no good reason why you'd normally start from the right, okay? So starting from the right, here's my interval from 2 to 3. A right-hand approximation says I'm going to start on the right side of the interval. If that's 2 and that's 3, the right side is over here at 3, and so that's where my rectangle is going to be. Now notice the difference already. You see how now we've gone above the function? So it looks like maybe this approximation is going to be an over-approximation. Let's stick with it and see. Let's go to my next rectangle, or my next subinterval. So I go from 1 to 2, the right side is 2. That y value is going to determine the height of my rectangle. Over here, my furthest left subinterval, 0 to 1, the right value is 1. And I don't mean correct, I mean right side. So that's going to be my rectangle. Okay? And right now, I hope you can already see why this is an over-approximation, because look, everything under the curve is covered by the rectangles. However, this is all above the curve. That's all extra area that we didn't need. This is just how the calculation goes. They're approximations. They're not exactly right, but they're close. Okay, so let's figure out what this is. So for this one, width of 1, height of natural log of 2. So 1 times ln 2. Over here, I have a width of 1. My height is natural log of 3, because remember, we're plugging in the 2 right there. 2 plus 1 is 3. So 1 times ln 3. And over here, I have 1 times ln 4. So those are my 3 regions. I'm going to add those up. So I've just got, they're all multiplied by 1. So what I'm typing in is natural log of 2 plus natural log of 3 plus natural log of 4. And when I do that, I get 3.18 as my total area. And so is that number too big or too small? I hope you can see that it's too big. Well, already, we found a left-hand approximation, which turned out to be too small, 1.79. We found a right-hand approximation, 3.18. So what we know is that the truth lies somewhere in the middle. Maybe it's 2.5 or something like that. I'm just kind of mental math, figuring out where the middle of those two would be. Now, we're not just going to average them, because it's not necessarily true that it's just the average of those. So these are two techniques we've learned. I want you to be thinking as we go along, what could we have done with this to make this a more accurate approximation? Because they're not super, super accurate yet. We're just learning the concept, but if we wanted to make it really accurate, what would we do? Eventually, we need to make them perfectly accurate. Okay? A couple more. Okay, now we're going to talk about something called a midpoint approximation. And so again, we have the same visual. Guys, in your notes, make sure you're putting down that it's called a midpoint. These aren't just like general ways, these are specific techniques that sometimes will be called out and you'll be asked to do a midpoint, asked to do a left or right hand sum. Okay, so take a look at the midpoints on these. Okay, so here we go. I'm going to have 1, 2, and 3 as my subintervals, and 0. The midpoint works a little differently. Now, when we started on the left, we'd find our interval, for example, 0 to 1, we'd start on the left, that's our rectangle. With the right hand, we'd find the right side of that interval. With the midpoint, we find the midpoint of that interval. So if this is 0 and that's 1, the midpoint is 0.5. So what we do is we go up from 0.5. That is the y value that defines our subinterval now. Let's go to the next one. This goes from 1 to 2. The midpoint is 1.5. I'm going to go straight up from 1.5. That is the y value that defines this subinterval. Look, I missed. I'll try again. Okay, and then down here, 2 and 3, the midpoint of 2 and 3 is 2.5, and so that is going to be the y value that defines our subinterval. Now, as we go, we should probably try to consider, is this more or less accurate than what we've done so far? So what I think I'll do is I'll do the over in green, and I'll do the under in the red. So what I mean by over is I mean things that are now covered by these boxes that are not actually underneath the curve. So right here is an example. Okay, this is an over because it's above the curve. We didn't want to shade that in, but it's being shaded in. Here's another one. Here's another one. In red, I'm going to shade the part that's an under approximation. So the parts that are missing is what I mean by that. So like right here, this area is underneath the curve, but it's not actually shaded in, it's not covered by a rectangle. But look at this. The green and the red, they're not exactly the same necessarily, but they kind of cancel each other out. That's different than what we've done so far. Before we were either just over or only under, but now we have both overages and undershades, and they kind of cancel each other out a little bit. And again, I'm not saying it's perfect. Oops, let me clean up this one over here. My illustration is not good enough. But they sort of cancel each other out, okay? And so maybe this is a more accurate method or more precise method for finding these areas. Let's actually find the areas. Now, the width of each rectangle is still 1. So I still have a 1 in there, 1, 1, 1. The heights are a little bit different because now that x value was 0.5. So if I had natural log of x plus 1, I'm putting in a 0.5 right there, so this is natural log of 1.5. The x value that we used here was 1.5, so I need the y value associated with that, so that's natural log of 2.5. And then over here I'm plugging in 2.5, and so that's natural log, add 1, of 3.5. Now before I type that in, let's make a prediction. The first approximation was too small, it was 1.79. Second one was too big, 3.18. Make a prediction about where you think this one will lie. Will it be bigger than both? Will it be less than both, the left and the right? Or will it be in between the left and the right? I'm going to type it in while you think about that. Okay, natural log of 1.5 plus natural log of 2.5 plus natural log of 3.5, and I get 2.57 when I do that. So it was in between them. It was greater than the right-hand approximation, or excuse me, greater than the left-hand approximation, less than the right-hand approximation. It's somewhere in the middle. And look, that kind of makes sense, because if these are canceling out, that should be the most accurate method so far. There is one more we need to talk about, and that would be the trapezoid rule. The trapezoid rule, and we're going to be consistent here. We're going to break up our axes the same way. So I'm going to break them up at 0, 1, 2, and 3. But the trapezoid rule is the only rule where we're not going to be using rectangles. One of the problems with rectangles is that when you place a rectangle on here, if you have something that's increasing or decreasing, the top of each of these rectangles is perfectly horizontal. And so it can't capture that increasing or decreasing behavior very well. A trapezoid, on the other hand, can. And so the trapezoid rule is going to be just a little bit more work. But we can do this. So for this interval, we're doing both the left and right approximations at the same time, sort of. So I'm taking the left y value and the right value, and I'm going to connect them. Okay, now that one's a triangle, right? But the next one will be a trapezoid. Okay, for the next one, I'm going to take the right y value and the left y value and connect them. And then I'm going to go like this. And so here now is a trapezoid. We've got two parallel sides. We've got the other two sides which are not parallel. That's trapezoid. Okay, let's put in the last one. So pick my y value. I'm going up from 3. Connect the dots. And now I've got two trapezoids and a triangle. So it's a little more work to find the area of a trapezoid. But do you think this is more or less accurate than what we've done so far? It's actually going to be pretty darn good, because look, there's very little space that I'm missing. It goes under the curve, so it is going to be an under approximation. My number's going to be a little bit too small, but man oh man, it's going to be really, really close. Before we do that, let's make sure we remember how to find the area of a trapezoid. I don't know why I drew a triangle. The area of a trapezoid, I think I was drawing the letter A and I just was thinking about geometry or something. The area of a trapezoid, recall from geometry, that's base 1 plus base 2 multiplied by the height, base 2, all divided by 2. Okay, so with that in mind, let's go through this now. This one's pretty easy. This one's a triangle. Base times height divided by 2. Base is 1, height is natural log of 2 divided by 2. Okay, we'll come back and type that in just a minute. Okay, this next one, this one is actually a trapezoid. I want you to remember where the bases are. The bases, and I will put them in blue if I can remember how to change the color. I can't find my colors. Oh, there's my colors. Okay, there's my blue. Okay, so I'll put it in color. The bases are these vertical sides. That confuses some people. They go, wait, but bases are at the bottom! Right, but the shape has been rotated, okay? So the bases are the verticals on this one. And so now let's fill in our formula. So what we have is the base, or excuse me, base 1 plus base 2. So base 1 is natural log of 2. Base 2 is natural log of 3. Remember, I'm putting a 2, same equation as before, natural log x plus 1. And I'm plugging in a 2 there. So natural log of 3 times the height. The height now is down here. So that's 1 divided by 2. Okay, let's fill in our last one. And so down here, what I'm going to get, I've got my two bases. So that'd be natural log of 3 plus natural log of 4 times the height. The height is that base, that's 1, divided by 2. Okay, so we've got all the rules set up. Now all we need to do is type them in. Okay, that's a little extra button pushing. I'm actually going to write out the decimals for each of these as I go. So I get natural log of 2 over 2 is 0.3, let's do to the hundred or to the thousands place, 0.347. Okay, what about this one? Natural log of 2 plus natural log of 3 times 1 divided by 2, 0.896. Okay, what about this one? Natural log of 3 plus natural log of 4. We're going to divide that by 2. And I get 1.242. Okay, so those are the areas of the individual subintervals. Now we're going to add those together. So plus 1.242 plus 0.896 plus 0.347, and I have 2.485. Plus 2.485. And I hope we believe that's a pretty good approximation, because visually it looks really, really promising. Okay, so that's our 4 different methods: left hand, right hand, midpoint, trapezoid. What was the actual answer? So I did this earlier with graphing software on a calculator with the TI Inspire, and I got 2.545. So this is quite close. This is also really close. Okay, so I hope you can see that, especially for the approximations, the midpoint and the trapezoid rule are preferred. They're much more accurate. Although AP testers, what I've noticed recently is a lot of times they're going to give you a table and ask for a left hand or a right hand. So you need to know how to do all of them. Okay, so let's go back to that question. How does changing the number of rectangles, and I asked this earlier, if I change the number of rectangles, or how could I make this more accurate? What we have on the screen right now is the same exact graph the same exact curve, 4 different times, and in each of them we have a different number of rectangles. I'm going to call that n. So here n equals 4, and here we have 1, 2, 3, 4, 5, 6, 7. We have 8 rectangles. Going down here, I'm not going to waste your time counting them in front of you, but that's a lot more rectangles. Then we have a whole heap of rectangles down here. So the question is, which one of these 4 is going to be the most accurate as far as the area under the curve? And notice down here, yeah, it does go below the axis. That can happen too. Haven't done it yet, but that's absolutely something that can happen. Okay, so which one's most accurate? Well, I hope you see that it's this one. Even when these rectangles go over or under, it's just little teeny tiny areas. It's just under or over by a little bit. It's not bad. Over here, oh my gosh, there's a big missing hunk right there. There's a huge overage right in here. Huge. This rectangle, very little of that rectangle is actually under the curves. That's not a very good approximation. We're getting better, better, best. So as n gets bigger, this gets more accurate. Now, what if we wanted it to be perfect? What would n have to be? It would have to be infinite. We'd have to just keep slicing rectangles all day long until this became perfect. Now that's not very practical. So when a mathematician finds something that's not practical, they have to either find new notation or a new way of expressing that or a new method. And that's specifically what an integral is. Okay? Because everything we've done so far has been discrete, chopping it up into 3 pieces or 4 pieces or 8 pieces. Okay? And this is all going to say the same stuff as I said before. That Reimann approximation is discrete. It's not continuous. Calculus is the study of continuous math. And so that's a problem. Okay? Now, from 1 to n is good. From 1 to infinity, that's what I was saying before, cutting it into infinitely many slices, but it's not practical. Okay? It doesn't work. So we need a better way of doing that. And so this is what we have that's better. Now this incorporates everything we've talked about so far. Okay, we've got limits, we've got sigmas, but check it out. So it's just that same definition of a Riemann sum we had. You've got your height, you've got your width. You're going to add up all the areas from 1 up to n. N is how many rectangles, and this says we want n to be infinitely big. We're just going to make it as big as we can, and the more we do that, the better it is. I'd like you to remember what that letter is. That's a sigma. And what letter is sigma? A lot of people say E. It's not E. It's the Greek letter for S. And they do that on purpose. It's chosen like that because it is a sum. And it's so we can remember, okay? Sigma, sum, they start with the same letter, there you go. And so that's going to lead us to our new form. Okay, this is discrete, this is now continuous. This is including those infinitely many rectangles. Okay, and so we call that an integral, bounded from a to b of our function, f of x, whatever it is, with respect to x. Okay, and that's a definite integral. This absolutely must be in your notes. And this a and b were the same exact things that we had a minute ago. So what I'd like you to think about is how does this relate to what we just did? Or how could we write out what we just were working on in this notation? And here it is. This was our function. Every time we started with an x value of 0, we went to an x value of 3, and we were using x on our x-axis. Sometimes that could be a t, for example. Like imagine you had a velocity function. Okay? Then you might have a dt at the end, because your independent variable is time. So it won't always be x, it could be all sorts of things. But this is another way of writing everything that we did in this video. Okay? Hope that's a good enough introduction for you for left-hand sums, right-hand sums, midpoint sums, and trapezoid sums, and that you now can produce those on your own.